Hi, and welcome to Engineering 255 Statics. In this episode, we will look at first the few sections of the Chapter 2, where the Chapter 2 is about force vectors. We'll look at 2.1 scalars and vectors to see the difference of these two. We will look at how you can do some operation about vectors and give you some example how you add assistant but coplanar forces, meaning the forces are acting on the same plane. So the objectives of this video is that you resolve a 2D vector into components, and also how do you add 2D vectors using the Cartesian vector notations, meaning how do you use x and y and z to do the operation. When we are in the lecture, we will do some more examples and we will do some group problem. Now first, let's take a look at what the difference between the scalar and vectors. It's important that you understand that scalar only has the magnitude. So it's only about the amplitude of a quantity, where the vector not only has the magnitude, but it also has a direction associated with that. We give you some example in a previous lecture. The quantity such as force is a vector because the direction of the force matters. If you think about the temperature, temperature is only a scalar because temperature doesn't care about temperature on the right or temperature on the left. There's no direction, specific direction associated with temperature. And when you do the operation, the scalar, you simply just do an arithmetic operation such as a plus and minus. You add the number or subtract the number. But in the vector, you cannot simply just add the magnitude. You have to treat it as a vector. When we represent a vector, we will use an arrowhead on top of that. So when you see that we put an arrowhead on top of this quantity, that simply means this is a quantity that has a direction associated with that. And that is the difference between the scalar and vectors. The section 2.2 give you brief introduction about the vector operations. We also mentioned this one in the previous one. It's a very simple, if you have a scalar multiplied with a vector, how do you do the operation? The quantity of the scalar simply represent, are you going to enlarge the vector or are you going to shrink the vector? If the value of the scalar is greater than 1, it means you're going to make the vector to be larger or longer. But if you make the quantity of the scalar to be less than 1, you kind of shrink or make it shorter of the vector. If you put minus sign, and it represents the direction is in the opposite direction. Now, how do we do addition if you wanted to add two vectors or more together? There's two different ways you can do it, and this way is not based on the calculation. Actually, you do this one by using a ruler. The first method is called the parallelogram law, which means you have two vectors, A and B. And you make the A and B connect together at the end point of each one of the vector. So they connect at this point right here. Once they are connected, then you draw the parallel line to each one of the vectors. So when you look at the A, and we draw a parallel line starting from the head of the B, and this is the line that parallel to A. You do the same thing with the parallel line of the B starting from the arrowhead of the A. And these two are going to intercept at the point of P. Your resultant vector, which is the addition of the A vector and the B vector, will be the vector starting from the intersection endpoint of both vector to the parallel line intersection point P at here. So that is what our resultant vector is from the A and B. The other way you can do it is so-called the triangle method. And you do similar thing. You starting from any of the vector. Let's say you start from vector A, and you have the vector A starting from this point to the head of this point. And let's just shift the vector B and make the vector B endpoint align with the vector A arrowhead. And you can see the two vectors will consecutively connected like this. Then your resultant vector is the vector from the starting point of A to the end point of B. That R is going to be the same as the parallelogram law, and it's the resultant vector that you can get. Certainly, you can start with the vector B. If you do that, it should give you the same answer as well. So that is how you can do a vector addition by using parallelogram or use the triangle law. If you have more than two, you certainly can continue doing that by finding the resultant of first two. Then you use the resultant, adding with the third vector with the same way, and you can find the answer as well. Another question that we sometimes want to consider is that if you want to subtract, what happened? Well, remember when you subtract, you simply just reverse the direction of the vector and you do the addition as well. So if you have A minus B, what do you do first? Well, you are going to reverse the direction of the B and you follow either the parallelogram or you use the triangle method to do the subtraction. And that is how you do the vector operation. There's another way to do the operation of the vector, which is that we can resolve a vector into components. And this is what we call a resolution. When you do a resolution of a vector, you are breaking a vector into the components. In this example, you can see we have a vector of f, which is a force. And we can decompose this or resolve this into two components, and in this case is the Fu and Fv. When you resolve this and you need two axes, in this case we have the axis of U, we have axis of V. Now in most of the case we like U and V to be perpendicular to each other, which has a benefit of doing the resolution, because when you are decomposed then into a perpendicular directions, they won't interfere with each other. So if you do decomposition, you have component of U, you get a component of V, you add these two together, supposed to give you the same vector of F as well, which is what the figure C is trying to tell you. And this is a very similar to like a reverse what we did before, where we have a two vector, we say we want to add them together, and we kind of draw the parallelogram, right? And which is like this one here, and you can find a resultant factor F. But here we are decompose the resultant vector into two vectors. So the last part of this chapter is that we are going to talk about how you add a system of copendent forces. And you just think about these forces or vectors. It's similar to what we just mentioned. Usually to do this in the calculation, we will resolve vectors. And we resolve the vectors into two components. As we said, it's better to decompose them into a perpendicular components. And the most common way is that we do horizontal and vertical axis, which we call X and Y. The Cartesian is the name that we use to name these X and Y coordinate system. Each of the component of the vector will have only the vector, only the magnitude, and a direction associated with that. And how do we represent the direction? We can use a small I here to represent direction in the x-axis. We can use y to represent the direction in the y-axis. And then the amplitude simply is represented by the f of x and f of y. The I and j are what we call the unit vectors. We're going to talk about unit vectors a little bit, which is associated with the position vector as well at the end of this chapter. Let's look at an example. Well, we have a force vector F. We want to decompose that into a Cartesian vectors. And we have two components, f of x, f of y. We have the unit vector of I and j. So instead of writing the f vector, we represent this one as two components. Each one component has its unique direction of I and j. And that's how we represent it. If you have another vector which is at a different direction, f plane, you can do the same thing. And it's really not necessary to make it as a horizontal and vertical. You can choose any direction, and as long as the other direction is perpendicular to each other, and then you can use that as a coordinate system as well. It is very useful sometimes when you change the orientation of the coordinate. Sometimes it can save your time to do the calculation, which we will show you in the future. So let's look at the addition of the several vectors. In this picture, we have three vectors. We have F1, F2, and F3. And we want to add them all together. We do the same thing for each one of the vector. By using the x and y in these pictures, we decompose them into smaller components. Once you do that, you can find out the amplitude of each one of the vector components in x and y directions. Once you decompose each one of the vector with the components, and it's very simple to do the operation, which you just simply sum the magnitude at each one of the direction together, and then you represent that as an overall vector to be the summation of the three components. So the Fr is the resultant force from the F1, F2, and F3, and the Frx and Fry are the components for the I direction and the J direction. Let's quickly review how we can represent a 2D vector with a magnitude and angle. Here you have a force F of R vector. We can decompose that in the x direction and y direction. And the component are Frx and Fry. The direction of the vector can be represented the angle between the positive x and the direction of your vector. So you see the vector angle is represented as the theta. In the trigonometry, we can find out the angle if we know the components. We take the uptangent of FRY divided by FRX, then we got the angle that is the tangent angle of this triangle here. If you know the components, you can also find the magnitude of the vector of f of r. This f of r here is not a vector, is the magnitude of the vector. So you just take the square root of the magnitude of the rx square plus magnitude of fy square. That's how you find the magnitude and angle of a vector of fr. All right, now let's look at one example here. How we do the vector, force vector addition in a two-dimensional coplanar system. In this example, we have three components, F1, F2, and F3. Each one of the force has different magnitude here. So the F1, F2, and F3, they're scalars, they're not vectors. However, they also give you the direction, and they represent direction in a different way. If you look at f of 1, it is just right on the y-axis. If you look at f2, it is on the second quadrant. It make the direction to the left up, and with a 45 degree is not respect to the positive x direction, is the negative x direction. Where the f of 3, they use a small triangle to represent the direction. It tells you if you look at the x component is 3 and y component is 4, and this is what we call the 3, 4, 5 triangle. With this information, we will be able to find out the angle of this vector, which is uptangent of fy divided by fx. Y is 4, x is 3. You do uptangent of this, you can find the angle from positive x to this vector. So, how we sum these three together? We decompose each one of these into xy component. So you resolve then into xy component, then you add the component at x together, and you add the component at y together, and that will be the resultant vector of x and y. Then if you want to find the vector of the resultant force, you have to find the magnitude and angle from the resultant components. Let's look at the detailed calculation. So f of 1, as we said, is on the y-axis. So y-axis is the j direction. So you have 0i plus 300j, and the unit is Newton. So we are representing this one as a vector, but in the x and y component, or the I and j component. For the f of 2, it's 45 degree with respect to the negative x-axis. This is the 450. So you have negative 450 because it's on the negative x direction. You do a cosine 45 degree. Cosine 45 degree, it's going to give you the component on the x direction. So this is a negative 450 cosine 45 degree I. And in the x direction is, in the y direction, it should be positive, is upwards as a 450 times sine 45 degree. So sine 45 degree is going to be this component here, right? And you can kind of shift this one to the y-axis, and that is the same as this one right here. And that is 450 sine 45 degree. Where f of 3 is use 3, 4, 5 triangle. So if you want to find a component in the x direction, you use 3 over 5. If you want to find the y component direction, you do 4 divided by 5. So here, this one is the y component, this is the x component, and you resolve that into these two components. And then we just simply sum those together. From the previous slide, we got the component for each one of the force, and you sum them all together. Remember, the first one doesn't have x component, you only have y, which is 300, and we add them all together. And the second force is on the second quadrant on the negative x direction, so you minus this amount, and you find the final component. For the F of R, the resultant force is 41.8 I and 1098 J. But we are more interested about how to represent this force in terms of the magnitude and angle. If that is the case, then you use the previous slide. Then we show you how to find the magnitude and angle. Then you take the square root of fx squared, right? Fx squared plus, oh, this is hard, f of y squared. You take square root of that, which is exactly what this one is trying to do, and you got 1099 Newton. For the angle, you take uptangent of f of y, which is 1098, divided by f of x, 41.8. You got this angle here. So this is the angle of theta, and this amount is the magnitude of this length at here. So that is how you do the calculation if you try to find the resultant force from the 2D plane.